Welcome! Today, we'll be solving LeetCode problem number 268, missing number. This is a classic problem that tests your understanding of array manipulation and mathematical reasoning. Let's dive into the details and explore different approaches to solve it. The problem we're solving is called missing number. Here's the setup. You're given an array called nums that contains n distinct integers. These integers are all within the range from 0 to n inclusive. However, one number from this range is missing, and your task is to find and return it. For example, if the numbers in nums are 3, 0, 1, then the missing number is 2. To clarify, the input is an integer array nums of size n where all the numbers fall within the range 0, n. The output is a single integer, which represents the missing number. Let's explore this with some examples. In the first example, the input array is nums equals 3, 0, 1. Here, n is equal to 3 because there are 3 elements in the array. The full range of numbers, from 0 to n, would be 0, 1, 2, 3. When we compare this full range to the numbers present in the array, which are 3, 0, 1, we can see that the number 2 is missing. Thus, the output is 2. Let's look at another example. This time, the input array is nums equals 0, 1. For this input, the array nums contains 2 elements, so n is equal to 2. The complete range of numbers from 0 to n is 0, 1, 2. The numbers in the array are 0, 1, which means the missing number from the range is 2. Therefore, the output is 2. Now, consider a larger array where nums equals 9, 6, 4, 2, 3, 5, 7, 0, 1. In this case, the input array has 9 elements, so n is 9. The full range of numbers from 0 to n is 0, 1, 2, 9. The numbers present in nums are 9, 6, 4, 2, 3, 5, 7, 0, 1. When we compare the two, we see that the number 8 is missing, so the output is 8. To summarize, the constraints for this problem are that the length of the array nums is equal to n, with n ranging from 1 to 10⁻4. Every number in the array is unique and falls within the range 0, n. Be mindful of edge cases, such as when the smallest number 0 is missing, or when the largest number n is missing. Arrays with only one element or numbers in a random order are also important to consider. To begin solving the missing number problem, the brute force approach is one of the most straightforward methods we can consider. The intuition behind this approach is simple. We iterate over the range of numbers from 0 to n, and for each number, we check whether it exists in the input array. If a number is not found, we return it as the missing number. The steps are clear. Loop through all integers from 0 to n, and for each integer, perform a membership check in the array using the n operator or its equivalent in other programming languages. This approach has a time complexity of O, n squared, since for each of the n numbers, we perform a linear search through the array. While the brute force method is conceptually simple and does not require additional memory, its inefficiency for large inputs makes it unsuitable for practical use cases where n is large. This quadratic time complexity is the main trade-off, making this approach more of a theoretical baseline rather than a recommended solution. An improvement over brute force is the sorting approach. By sorting the array, the numbers are arranged in ascending order, enabling us to efficiently identify the missing number. The key idea here is to compare the indices of the sorted array with the values at each position. If there is a mismatch between an index and the corresponding value, that index represents the missing number. If no mismatch is found during the traversal, it means the missing number is at the end of the range, which is n. The sorting step dominates the time complexity at O, n log n, while the traversal is linear. Depending on the sorting algorithm used, the space complexity can either be O1 for in-place sorting or O(n) for algorithms requiring extra memory. While this approach is an improvement over brute force, it is still not optimal due to the sorting cost. However, it offers a more feasible solution for moderately sized inputs. A highly efficient and elegant solution involves using a mathematical formula. The intuition behind this approach is based on the formula for the sum of the first n integers, which is given by s equals n asterisk, n plus 1, / 2. By computing this expected sum and comparing it with the actual sum of the elements in the array, we can easily find the missing number as the difference between these two sums. The steps are straightforward. First, calculate the expected sum using the formula. Next, compute the sum of all elements in the input array, and finally, subtract the actual sum from the expected sum to determine the missing number. This method is incredibly efficient, with a time complexity of O(n), since we only need a single pass to compute the sum of the array, and a space complexity of O(1), as no additional data structures are required. This approach leverages the arithmetic properties of integers to deliver optimal performance, making it both simple and powerful. Another efficient technique for solving this problem is the XOR approach. This method utilizes the properties of the XOR bitwise operation, which is particularly well suited for detecting missing or duplicate numbers in sequences. The key insight here is that XORing a number with itself results in 0, and XOR is both commutative and associative. By XORing all integers from 0 to n with all elements in the input array, the repeated numbers cancel out, leaving only the missing number. The process involves initializing a variable to 0, XORing all numbers in the range from 0 to n, and then XORing all elements in the array. The final result is the missing number. This method is highly efficient, with a time complexity of O(n), due to the linear traversal of the range in array, and a space complexity of O(1), as no additional memory is required. While this approach is fast and resource efficient, it might be less intuitive for those unfamiliar with bitwise operations, making it slightly harder to understand and implement. Among the various solutions, the mathematical formula approach stands out as the chosen strategy for solving the missing number problem. This method is favored for its simplicity, efficiency, and clarity. With a time complexity of O(n) and a space complexity of O(1), it meets the optimal performance criteria while remaining easy to implement and understand. Unlike alternative methods, it avoids the overhead of sorting or the complexity of bitwise operations. The brute force approach, while intuitive, is far too slow for large inputs due to its O(n)² time complexity. Sorting, though better, still incurs an O(n log n) cost, which is unnecessary given the existence of linear time solutions. The XOR approach, while equally efficient, is less intuitive and may pose challenges during debugging or explanation. The key insight here is the use of the sum formula for the first n integers, which allows us to directly compute the missing number by subtracting the actual sum of the array from the expected sum. This simplicity and elegance make it the ideal choice for this problem. While the mathematical formula approach is optimal for the given problem, it does come with certain trade-offs. One limitation is its lack of flexibility in handling variations of the problem, such as scenarios involving negative numbers or duplicate values. The formula assumes a perfect sequence of integers from 0 to n, so any deviation from this structure would render the solution ineffective. However, within the problem's stated constraints, this approach strikes the best balance between simplicity, performance, and clarity. It avoids the inefficiencies of brute force and sorting while being more intuitive than the XOR method. Ultimately, the mathematical formula approach is a clear winner for this specific use case and demonstrates the power of leveraging arithmetic properties to solve algorithmic challenges efficiently. To solve the missing number problem, we start by understanding the input and the task. The array nums contains n distinct numbers drawn from the range 0, n. However, one number in this range is missing, and our goal is to identify that number. A straightforward approach is the brute force algorithm. First, we define the range of numbers, which includes all integers from 0 to n. While the range has n plus 1 numbers, the array nums only holds n elements because one number is missing. Next, we iterate over the entire range, 0, n. For each number in this range, we check whether it exists in the input array nums. This is done using a membership operation, such as the in keyword in Python. If we find a number in the range that is not present in nums, then this number is guaranteed to be the missing one. Once we identify the number that is missing during our iteration, we simply return it as the result. This brute force method ensures correctness because it systematically checks every number in the valid range, 0, n, without making any assumptions about the order or structure of the input array. A key insight here is that the algorithm relies on exhaustive search, which guarantees that no number is overlooked. However, this approach comes with a computational cost. Checking whether a number exists in an unsorted array, like nums, is an O(n) operation. Since we repeat this membership check for each of the n+1 numbers in the range, the overall time complexity is n squared. While simple and effective, this quadratic complexity makes the brute force approach inefficient for larger input sizes. This algorithm naturally handles various edge cases. For example, if the missing number is 0, it will be correctly identified since 0 is explicitly included in the range 0, n. Similarly, if the missing number is n, it will also be identified because the range includes n as well. Even for small arrays, such as when nums contains only one element, the algorithm functions correctly. For example, if nums equals 0, the range iteration will determine that 1 is missing, and if nums equals 1, it will identify 0 as the missing number. Additionally, the algorithm relies on two key data structures, the input array nums, which stores the given distinct elements, and the loop variable I, which represents the current number being checked in the range. Membership checks are performed directly against the nums array without requiring additional data structures. The algorithm's core operations revolve around range iteration and membership checks. By iterating over the range 0, n, the algorithm ensures that every valid candidate for the missing number is considered. For each number in the range, the membership check determines whether it exists in the input array. This is achieved using the operation I in nums. If the number is absent from nums, it is immediately identified as the missing number and returned. This return statement ensures that the algorithm terminates as soon as the missing number is found, making the process efficient in terms of execution flow. The correctness of the algorithm is guaranteed because the range 0, n accounts for every possible number, and the array nums contains all but one of them. Therefore, the missing number will always be identified during the iteration. While the brute force approach is simple and correct, it does have limitations. The main drawback is its time complexity of n squared, which arises from the nested operations of iterating over the range and performing membership checks for each number. This quadratic complexity makes the algorithm impractical for large input sizes. On the other hand, the space complexity is 1, because no additional data structures are used beyond the input array and loop variable. To optimize this solution, we can reduce the time complexity by using a hash set for membership checks. With a hash set, the membership operation becomes 1, reducing the overall time complexity to n. Alternatively, mathematical approaches, such as summing the expected range and subtracting the sum of the array, or using XOR-based techniques, can achieve an n solution without additional space, making them highly efficient replacements for the brute force method. This solution leverages the mathematical property of arithmetic sequences. The array contains numbers from 0 to n, with 1 missing. The sum of the first n natural numbers can be calculated using the formula n asterisk, n plus 1, // 2. This gives us the expected sum if no numbers were missing. We then compute the actual sum of the given array using Python's built-in sum function. The difference between the expected sum and the actual sum directly gives the missing number since every other number cancels out. This approach is highly efficient with a time complexity of n for summing the array and a space complexity of 1, as it uses only a few variables for calculation. This is the Java implementation of the LeetCode problem number 268, missing number. The logic mirrors the Python solution, using the formula for the sum of the first n natural numbers to calculate the expected sum, then subtracting the actual sum of the array to find the missing number. The Java implementation uses explicit type declarations for each loop for summing the array elements, and adheres to standard Java conventions. Here, we begin with the array nums equals 3, 0, 1. This array contains numbers ranging from 0 to n, where n is equal to the length of the array. Since n equals 3, the numbers should range from 0 to 3. However, one number is missing, and that's what we need to find. To do this, we first calculate the sum of all numbers from 0 to n using the formula for the sum of the first n natural numbers, total_sum equals n asterisk, n plus 1, // 2. Substituting n equals 3, we find that total_sum equals 6. This represents the sum of all numbers from 0 to 3. Next, we calculate the sum of the numbers actually present in the array, which is actual_sum equals sum, 3, 0, 1 equals 4. Now, to find the missing number, we subtract the actual_sum from the total_sum. This gives us missing underscore number equals total underscore sum actual underscore sum equals 6, 4 equals 2. So, the missing number in this case is 2. Let's try another example. Here, we have nums equals 0, 1. This array has a length of n equals 2, meaning the numbers should range from 0 to 2. Using the same formula for the sum of the first n natural numbers, we compute the expected sum as total underscore sum equals n asterisk, n plus 1, / 2. Substituting n equals 2, we calculate total underscore sum equals 3. This represents the sum of numbers from 0 to 2. Next, we calculate the sum of the numbers in the array nums. Here, actual underscore sum equals sum, 0, 1, equals 1. To find the missing number, we subtract the actual underscore sum from the total underscore sum. This gives us missing underscore number equals total underscore sum actual underscore sum equals 3, 1 equals 2. So, the missing number in this case is also 2. Now, let's consider a more complex example. Nums equals 9, 6, 4, 2, 3, 5, 7, 0, 1. This array has a length of n equals 9, meaning the numbers should range from 0 to 9. To calculate the expected sum of numbers from 0 to n, we use the same formula, total underscore sum equals n asterisk, n plus 1, / 2. Substituting n equals 9, we find that total underscore sum equals 45. Next, we calculate the sum of the numbers present in the array. Here, actual underscore sum equals sum 9, 6, 4, 2, 3, 5, 7, 0, 1 equals 37. Finally, the missing number is computed as missing underscore number equals total underscore sum actual underscore sum equals 45, 37 equals 8. Thus, the missing number in this example is 8. By following this systematic approach of calculating the expected sum, summing up the array's contents, and finding the difference, we can efficiently determine the missing number in any given array. The solution to LeetCode problem number 268, missing number, has a time complexity of O(n). Let's break this down step by step. First, calculating the length of the array using len, nums, takes constant time, or O(1), because determining the length of a list in Python is a simple operation. Next, computing the expected sum using the formula n asterisk, n plus 1, / 2 also takes O(1), as it relies on a few basic arithmetic operations, multiplication, addition, and division, all of which are constant time. Then, we calculate the actual sum of the array using Python sum function. This function iterates through each element of the array once, so for an array with n elements, the sum operation takes O(n) time. Finally, subtracting the two sums to find the missing number is a simple subtraction operation that takes O(1). When all these steps are combined, the dominant operation here is the sum function, which makes the overall time complexity O(n). Since the most time-intensive operation in this solution is the sum nums function, which iterates through the entire array, the overall time complexity is dominated by this step and is therefore O(n). Now, turning to space complexity, the solution uses a constant amount of additional memory, making the space complexity O(1). Here's why: the algorithm only uses a few scalar variables, such as n, total underscore sum, and actual underscore sum, each of which requires constant space. Additionally, no auxiliary data structures, like arrays or dictionaries, are used. The solution operates directly on the input array, performing arithmetic calculations without allocating extra memory. As a result, the memory usage remains constant regardless of the size of the input array, leading to a space complexity of O(1). When comparing this solution to a brute force or naive approach, the efficiency becomes even clearer. A naive solution might involve iterating through all numbers from 0 to n and checking if each number exists in the array. This would involve a nested iteration, one loop for numbers 0 to n, and for each number, another loop to check its presence in the array. This results in a time complexity of O(n squared, since each check is O(n), and there are n numbers to check. By contrast, the provided solution eliminates these repeated checks by leveraging the mathematical formula for the sum of the first n integers. This reduces the time complexity to O(n). To confirm the big O mathematically, we note that the dominant step is the sum nums operation, which iterates through the array once. Adding up all the constant time steps in this O(n) operation, the total time complexity simplifies to O(n). Similarly, because no extra memory is allocated apart from a few scalar variables, the space complexity remains O(1). Analyzing the best, average, and worst-case scenarios, the time complexity remains O(n) in all cases. In the best case, the algorithm still needs to process all elements in the array to compute the sum, as there's no way to shortcut this calculation. Similarly, in the average case, the time complexity doesn't change because the algorithm's steps are not influenced by specific input patterns. For the worst case, even with the largest possible input within constraints, the algorithm consistently involves a single traversal of the array, making the time complexity O(n). To summarize, this solution is optimal with a time complexity of O(n) and a space complexity of O(1). It is far more efficient than the brute force approach, as it leverages mathematical properties to achieve linear time without extra memory overhead. This makes it highly suitable for large input sizes, minimizing both computation time and memory usage. When tackling the missing number problem, there are a few common mistakes to watch out for. One frequent issue is off by 1 errors. This happens when you forget that the range includes both 0 and n, not just 0 to n1. If you miss the n value, your result will be incomplete. To avoid this, ensure your loops or checks explicitly account for n. Another mistake is relying on inefficient duplicate checks, like using nested loops or repeatedly searching for values in a list. These approaches can quickly escalate the time complexity to O(n squared). Instead, use a set to perform O(1) lookups. Lastly, edge cases like an empty array or an array with only one element are often overlooked. If these aren't handled explicitly, your solution might fail, so make sure to account for them in your implementation. Another pitfall to be aware of is not validating the input. If you assume the array always contains numbers in the range 0 to n without duplicates, you might encounter unexpected behavior when constraints are violated. To prevent this, consider adding validation checks if the scenario allows. Additionally, some people resort to sorting the array to locate the missing number. While this may work, it unnecessarily increases the time complexity to O(n log n). Instead, opt for mathematical or XOR-based solutions that achieve O(n) efficiency. From an interview perspective, understanding constraints is critical. Always clarify whether the input guarantees unique numbers in the range 0 to n, as this will guide your choice of algorithm. Interviewers also expect you to aim for optimal solutions, preferably O(n) time with O(1) space. Demonstrating awareness of edge cases, like empty arrays or single-element arrays, shows your attention to detail. Finally, being able to discuss trade-offs between approaches, such as numerical stability in the sum method versus readability, can highlight your depth of understanding. The concepts in the missing number problem are closely related to other problems on LeetCode. For example, in problem 136, single number, you identify the unique number in an array where every other number appears twice. Problem 442, find all duplicates in an array, focuses on detecting duplicates while maintaining O(n) time complexity. Similarly, problem 448, find all numbers disappeared in an array, involves identifying missing numbers within a range. Lastly, problem 287, find the duplicate number, challenges you to find a duplicate while adhering to O(n) time and O(1) space constraints. Exploring these related problems can deepen your understanding of number manipulation techniques. Beyond these, it's also helpful to familiarize yourself with alternative approaches to solve the missing number problem, as they often come with unique trade-offs. There are several approaches you can use to solve this problem, each with its own advantages and trade-offs. The mathematical sum formula is both simple and efficient, running in O(n) time with O(1) space. However, in certain programming languages, it may be prone to integer overflow, so that's something to keep in mind. The XOR approach is another excellent solution. It avoids overflow issues and also operates in O(n) time and O(1) space, but it might be less intuitive for some people to explain in an interview setting. Hashing, which involves using a set, is straightforward to implement and ensures O(n) time complexity. However, it requires O(n) extra space, making it less efficient than the sum or XOR methods. Lastly, while sorting the array is conceptually simple, it increases the time complexity to O(n log n), making it a suboptimal choice for most scenarios. It's important to weigh these trade-offs when deciding which method to use, especially in an interview or constrained environment. Great job! We've covered the missing number problem and explored how to approach it efficiently. Remember to practice similar problems to strengthen your skills. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!